You can stand on a dry, wind-scoured slope, hundreds of meters above the ocean below. There is no beach, no waves, no visible sign of the sea. And yet, if you bend down and pick up a rock beneath your feet, you are not holding volcanic stone or weathered gravel. You are holding marine coral, not fine beach sand blown inland, not lightweight shell fragments carried by a storm, but heavy, wave-rounded coral rubble, material that forms only at sea level,
This fragment of
on living
shows
reefs.
early signs of bleaching,
And here it
which
is,
why preserving the wider reef
sitting
is
hundreds
so
of meters above the ocean, on a volcanic island in the middle of the Pacific. The moment you accept that these rocks are real, that they are in place, and that they are unquestionably marine, only one question remains. What kind of wave could have put them there? Human intuition versus geological reality. When we think about tsunamis, we usually think about earthquakes. Japan, 2011. The Tohoku tsunami. Waves tens of meters high, devastating coastal communities. It was one of the largest disasters in modern history, with local run-up heights of around 40 meters. That event involved thousands of kilometers of fault rupture and the release of energy on a continental scale. But what happened in Hawaii was something very different. There was no major fault rupture, no plate boundary, no massive earthquake. The driving force here was something far simpler: gravity. The evidence in the rocks, the Hulapoe gravel, on the island of Lanai. Geologists identified a remarkable deposit, known today as the Hulapoe gravel. This deposit is anything but subtle. It is a chaotic mixture of broken coral, limestone blocks, volcanic basalt, and marine fossils from different water depths. These materials are plastered across slopes and ridges, at elevations of 300 to 370 meters above present sea level. Even more important is how this deposit was formed. Within it, geologists observed clear grading, imbrication of clasts, and flow indicators pointing inland, not downslope. If this material represented an uplifted shoreline, we would expect neat marine terraces and reef structures preserved in place. If it were storm-related, the deposits would thin rapidly inland and stop at elevations consistent with even the strongest cyclones. Instead, the material climbs uphill. All of this points to one conclusion: a single, extremely energetic flow arrived catastrophically, surged inland and upslope, and then drained back toward the sea. The evidence in the rocks, the Hulapoe gravel, on the island of Lanai. Geologists identified a remarkable deposit, known today as the Hulapoe gravel. This deposit is anything but subtle. It is a chaotic mixture of broken coral, limestone blocks, volcanic basalt, and marine fossils from different water depths. These materials are plastered across slopes and ridges, at elevations of 300 to 370 meters above present sea level. Even more important is how this deposit was formed. Within it, geologists observed clear grading, imbrication of clasts, and flow indicators pointing inland, not downslope. If this material represented an uplifted shoreline, we would expect neat marine terraces and reef structures preserved in place. If it were storm-related, the deposits would thin rapidly inland and stop at elevations consistent with even the strongest cyclones. Instead, the material climbs uphill. All of this points to one conclusion: a single, extremely energetic flow arrived catastrophically, surged inland and upslope, and then drained back toward the sea. Why not uplift OR storms? Scientific skepticism is essential, and this interpretation has faced it. The first alternative explanation is tectonic uplift. But Hawaii is not located on a plate boundary. There is no known mechanism capable of lifting coastal deposits hundreds of meters without leaving abundant coastal markers along the way. In fact, independent evidence from submerged reefs and drowned shorelines shows that these islands have been subsiding, not rising, over the relevant time period. The second alternative is storms. But the physics of ocean waves imposes hard limits. Even the most powerful cyclones cannot generate the sustained, coherent flow required to transport multi-ton coral blocks hundreds of meters uphill across complex volcanic terrain. The energy budget does not work, and the sedimentology does not match. When all other explanations fail, only one remains: an extreme tsunami. Not just one island. Similar high-elevation marine deposits are not confined to Lanai. On the island of Molokai, particularly along slopes facing the open Pacific, marine gravels and coral-bearing units appear at similarly inexplicable elevations. Their distribution is irregular. Some slopes were heavily impacted. Others were barely touched. This kind of selective, chaotic pattern is characteristic of tsunami behavior. Unlike storms, tsunami waves refract, wrap around islands, and focus energy unevenly, depending on underwater and coastal topography. The true source: volcanic collapse, 7:20 to 9 o'clock. The source of these waves lies offshore, hidden beneath thousands of meters of water. The Hawaiian Islands are only the exposed summits of enormous submarine volcanoes. And like all tall, steep volcanic edifices built on weak foundations, they fail. Sometimes slowly, sometimes catastrophically. One of the largest known submarine landslides on Earth is the Nuuanu landslide off the coast of Oahu. Its debris field covers an area larger than the state of California, with individual blocks tens of kilometers long. When a mountain-sized section of a volcanic island detaches and accelerates downslope almost instantaneously, the ocean does not ripple. It heaves. A scale that makes geologists uncomfortable. 9 o'clock to 10:30. Numerical models based on the volume and geometry of these Hawaiian landslides consistently show that initial wave heights could exceed 100 meters near the source. When those waves encountered nearby volcanic islands, run-up heights were dramatically amplified. Conservative estimates, based on the lowest confirmed marine deposits, place run-up on Lanai at more than 170 meters. More aggressive interpretations, incorporating the highest outcrops and flow indicators, push that number toward 300 meters or more. Even the lowest defensible values far exceed anything produced by historical earthquake tsunamis. Could this happen again? In principle, yes. Hawaiian volcanoes are still growing, still spreading, and still deforming. The south flank of Kilauea, for example, is slowly creeping seaward today at measurable rates. Most of this motion is gradual, accommodated by earthquakes and slow deformation. But the geological record shows clearly that slow movement does not rule out sudden collapse. That said, events capable of generating waves 200 to 300 meters high are extraordinarily rare. Their recurrence intervals are measured in tens to hundreds of thousands of years. The core message: this story is not really about Hawaii alone. It is about the upper limits of what the Earth can do when gravity, geology, and water collide. The Hawaiian Islands simply happen to be one of the few places where the evidence survived, perched high above the sea, quietly contradicting our intuition. And in the end, when you see coral on a mountaintop, you are forced to accept that the Earth has done the unthinkable.